Bismillahirrahmanirrahim. We continue our discussion on deadlocks in this lecture and see how deadlock avoidance algorithm works. We will continue our discussion in this lecture from methods for handling deadlock and deadlock avoidance method will be continued here. Let's now come to deadlock avoidance algorithm. It is also known as Banker's algorithm. This algorithm works for the multiple instances of resources. It is required for every process to declare maximum number of resources it would require in advance. When a request is submitted by a process, if resource cannot be immediately assigned, so process may have to wait. When process gets all its required resources, so the process must return all of them after utilization in a predefined time. Here is the example of Banker's algorithm. Keep in mind that Banker's algorithm works for the multiple instances of the resource. So for example, there is a resource in the system having 12 instances and 3 processes are there, P1, P2 and P3. All of these processes have in advance declared their maximum demands. P1 would require 10 instances of the resource, P2 would require 4 instances, and P3 would require 9 instances of the resource. If we add all these demands, so that would be more than the available number of instances. The available number of instances is 12 for the resource, while the total demand of 3 processes make 23. So practically, the demands are unable to be fulfilled at once. So every process will be assigned few instances at the beginning and rest will be assigned when they are available. Let's suppose initially P1 is assigned 5 instances, P2 is assigned 2 instances, and P3 is also assigned 2 instances of the resource. This information can be seen in the table above. So the highlighted table would give you these assignment information. Now let's see how operating system ensures a safe sequence and when the sequence goes unsafe. As you can see in the table as highlighted, the remaining needs are mentioned after initial assignments to processes. And the remaining instances of the resources is also mentioned. System have 3 available instances of the resources which can still be distributed among processes. So, if process P1 is further given 1 resource, its remaining request would reduce to 4. See the first assignment sequence. The one I highlighted. So if one resource is assigned to process P1, its remaining resource request would reduce to 4 and remaining instances of resource will also reduce to 2. If these two remaining instances of resource are assigned to process P2, whose remaining demand is also of 2 instances, so all the demands of P2 would go to complete, but the system will be left with 0 instances of the resource. P2 would complete its execution, utilize the resource, and would release 4 instances of the resource. These 4 instances would then be assigned to P1, whose demand also go to complete, and after utilization, it would release 10 instances of the resource. From these 10 instances, the demand of P3 can be completed, who require 7 more instances of the resource, and hence the system stays in safe sequence. But on the contrary, if you see the table below, let me highlight it. The distribution is in the form given in this highlighted table. P3 has been assigned one resource whose demand reduces to 6, and system has 2 further available resources. If all the 2 remaining resources are assigned to P2, whose demand goes to complete, and after utilization it would release 4 resources. But 4 resources are not enough to complete demands of neither P1, who requires further 5 instances, nor P3, who further requires 6 instances. Hence, the system goes in unsafe state, and it may enter in deadlock. So the resources are assigned in such a manner the system remains in safe state. Deadlock detection works to look for circular weight in the resource allocation graph. After detection of deadlock, we would look for the schemes to recover from deadlock. For the single instance of resources in the resource allocation graph, we would try to reduce it to wait for graph. The corresponding wait for graph is developed from resource allocation graph by eliminating resources and connecting processes, such as process Pi is waiting for a resource held by process Pj. So an edge from Pi to Pj will be drawn. Then circles in the wait for graph will be detected to check if the system is in deadlock or live lock. This is how we convert resource allocation graph to corresponding wait for graph. As you can see, we have only eliminated the resources from the resource allocation graph and connected the processes with each other. So the graph has become shorter and easy to locate the circles in it. You can see there are 2 circles in the corresponding wait for graph, one from process P1, P2, P3, P4 and back to P1. Let me highlight this. So, first circle involving 4 processes, and another circle is between P1, P2, P4 and back to P1. Let me highlight it also. So these are the 2 circles which you can easily draw. By now we have studied what a deadlock is and different methods to handle deadlock that include deadlock avoidance and deadlock prevention. Now is the time to apply different deadlock detection techniques. Operating system has few deadlock detection mechanisms that it applies on different cases. But before that, I need to remind you that we have 2 different types of resources. A resource may have a single instance, that means a resource may have single copy, such as you have single keyboard in your system, you have single printer. So these resources have single instances, single copies. While some resources may have multiple instances or multiple copies that include memory. So memory is a single resource, but it has different copies, such as primary memory and different types of secondary memories you normally use. So for both types of resources, operating system applies separate deadlock detection techniques. For the single instance of resource, commonly wait for graph is drawn in either to locate the circles. We have already discussed the wait for graph in previous slide. So, circles are detected in the wait for graph, and keep in mind every circle is not a deadlock. So we need to look deep into the circles if there are any deadlock breakers present or not. So if there are some deadlock breakers, that means this deadlock is not actively a deadlock, rather it's a live block. But if there are no deadlocks or circular breakers, then it is a deadlock. So for single instance of resource, normally wait for graph are drawn in order to find out the deadlocked circles. While for the multiple instances of resource, normally the banker's algorithm is applied. We have discussed the banker's algorithm in detail in previous lecture. We have seen practically with some example how banker's algorithm help in deadlock detection. So you can find out its details in the previous lecture. So now you must be clear, deadlock detection techniques works in 2 forms. One form is for the single instance of resource, and that is wait for graph. And other form is for the multiple instances of resource, and that is the banker's algorithm. Now we are going to discuss next topic, that is recovery from deadlock. This is our last topic of this chapter, and we need to find out if our system has been stuck in deadlock. So can there be any mean or any mechanism or any strategy by which we can recover our system from this deadlock? So let's see what can be the possible recovery schemes. By now we have discussed
What is a deadlock? How it is created? And what are the possible mechanisms or methods to handle deadlock? We have discussed different deadlock handling techniques such as deadlock prevention and deadlock avoidance, as well as methods for detecting deadlock. So now is the time that we have discovered there is a deadlock in our system. So how we can recover our system from this deadlock state? Since we have already said deadlock is a problem for operating system. So for recovery from a deadlock, operating system offers two methods. First one is process termination. Operating system can abort or terminate all deadlocked processes, or it can abort one process at a time until the deadlock cycle is eliminated. So, the process termination mechanism works either on a single process stuck in deadlock or all the processes stuck in deadlock. Operating system may either abort all the deadlock processes, or it can abort one process at a time until the deadlock is eliminated. But the question here is, if many processes are stuck in deadlock, so which process should be first selected as a victim to be terminated? The selection of process as a victim is normally done by different methods. Operating system has different options to choose a victim process, such as operating system can check the priority of the process. A higher priority process will not be terminated. Instead, a low priority process will be selected as a victim to get terminated. Another criteria for selection of victim may be on the basis of the use of CPU time. How much time a process has spent on CPU and how much more time it requires on CPU. So if it has spent more time on CPU and requires less time, more, so terminating such a process may be expensive for operating system. Now next criteria may be on the basis of the resources a process has already used, or the number of processes, the number of resources a process further need to complete its execution. If a process has used less number of resources and requires more number of resources further to complete its execution, so terminating such a process would be less harmful as compared to the one who has used more number of resources and requires less number of resources further for its completion. Another criteria that operating system has to consider is if the victim process is either interactive or batch. If the process is interactive or batch, this is an important criteria to decide which process should be selected as a victim. Since terminating an interactive process may be expensive as compared to batch process. Since the interactive process will come again and would require interaction from the user. while the batch process does not require any sort of interaction with the user. And another important property is that operating system also has to decide how many processes will require to be terminated in order to recover the system from deadlock. So these are some of the criteria for recovery scheme. If the system is stuck in deadlock, so operating system has to select which process should be terminated in order to recover the system from deadlock. But before selecting the victim, these criteria need to be evaluated. The next deadlock recovery mechanism or scheme is resource preemption. First one was process termination, we discussed in previous slide. So now is the resource preemption. Operating system has to recover from the deadlock, and for that operating system has to terminate one or few processes. That means all their held resources need to be preempted. So the selection of victim is made on the basis of different criteria as we discussed in previous slide. So a victim is selected using such a criteria that would be less expensive for operating system. That means it must incur least or minimum cost for operating system. The process which is selected as a victim gets rollback to some safe state, and it would resume all its operations or restart all its operations again. It is important to keep in mind the starvation factor. When a victim is selected for termination, the starvation factor is very important to be considered. Because if a process is always selected as a victim to be terminated, it would never get completed, and that would result in its starvation. That means that specific process will never get a chance to complete its execution. So operating system has to keep in mind that no single process is always get victimized to be eliminated from the system, so that all the processes are having equal chances to be selected as a victim, and no process can suffer from starvation. Here we come to the end of this chapter. I hope you have understood what a deadlock is, how we can draw a deadlock, what are different methods to handle deadlock, and what are the possible schemes to recover from the deadlock. We will proceed our discussion on next chapter in next lecture. That is all for now. I thank you all.